So let's take a mental look at this one. This is the extra problem that I handed out the other day. I sent out on the group meeting. So first, let's just start off by taking a look at what we want to go about this. We want to solve for the current and the voltage on each resistor and the power. So basically, we have our resistance values. We need to find the other numbers that we can use. So the first thing we really want to look at is what we can combine down. And we're going to start by doing these two, this group, and this whole group. We're going to combine these down, so technically we'll just have a fictional resistor there, which we'll put that in red. Whenever we have a fictional resistor, we'll draw it in red. So we'll use the reciprocal formula up here. So 1 divided by 10 plus 1 divided by 20, and 1 divided by that, 0.666 repeating. So that's going to be our fictional resistor for this guy up here. Essentially what we're trying to do with this is we're trying to break it down into a simple series circuit, which, if you remember doing the series circuits, what we're getting to is we're going to be able to find our voltage drop. That's going to give us our voltage on these two groups, which we know is constant in a parallel circuit. Once we have the constant for the parallel circuit, we'll be able to solve for the rest of the stuff. We'll have every number that we need. We'll have the voltage on all these. So for this one, we got 6.667. We'll round to that. And let's look at this one down here. We want to come up with this value right here for this fictional resistor, which is just basically using the reciprocal formula again. I'm getting 3.370, which makes sense. It's lower than the lowest resistor, which is always what we should be looking for. 6.67 ohms is lower than the lowest resistor up here, so it should be the same down here. I'm throwing letters next to them because I'm storing the whole numbers in my calculators, which is something you should try to get into the habit of doing. So now, ignoring this and this part up here, we have 1, 2, 3, 4, 5 resistors just in series. So now we can solve for our RT. So that comes out to be 200.037 ohms. Now remember, I didn't round any of my numbers off. I kept the number in its entirety because I wanted to be able to keep it as accurate as I possibly can. So now we know our resistance total, we know our voltage total. So E divided by R equals I. So 3,000 divided by our RT of 200, IT is equal to 14.997. Well, now that we have our current, we know that's constant in this circuit. No matter where we measure through our fictional resistors here, it's going to be there. So, with that knowledge now, we can actually go ahead and pull up our voltage drop for every resistor in here. And once we have that, we're golden. We have everything we need to do every single part of this. So how do we go about that? It's going to be I times R. Our current times our resistance is going to give us our voltage. Let's see here. So, this 14.997 times this is going to give us 99.989 volts. That's what we're dropping across. We know it's constant because this is connected to the same point. The resistors are connected to the same point, so they're going to see the same voltage. So this is going to be our voltage drop at that set of resistors, which, looking at it, it's not a whole lot. It's a very small number compared to our voltage. Very small resistance there. Makes sense. That number makes sense. So we're going to continue on, take our current, multiply it by this resistor right here. We're rounding out to 3 places on these. Not too bad, pretty straightforward. And this one, we're going to come out and it's going to read out to 50.552 volts. This one over here, we're going to be dropping quite a bit at, which makes sense, being it's the largest resistor, it's going to oppose it the most. It's going to have the highest power too. It should have the highest power. Just something to keep in mind as you're working through these. Some of these numbers should start to kind of jive you. So just for shits and giggles, let's add these up and see if we're at this number over here. See if we're at our voltage supply. Well, I'm at 2999.998. So I'm 2/10 off from having that. So I know those are good numbers. Well, now we've given ourselves pretty much everything we need. We have our voltage and our resistance. So we have 2 values for everything. We can solve for everything now. So it's pretty straightforward on this stuff. It's a lot of steps though. And you got to watch the steps, and that's why double checking these numbers is so important. If you mess up one of these calculations and you're way off from this, you need to restart and figure out where you made a mistake. So let's go on to the next part, because we want to solve for every single part of this problem. Every part of it we want to have the answer for, so we're going to go through it and figure it out. The next part that we want to look at is, let's just go right ahead and jump in and solve for power. So we could take E squared divided by R to solve for it, or we could figure out the current on each leg, which we need later. But let's just go with E squared and go that route. And just for starters, let's actually take this and actually come up with what our total power would be from this calculation, so we have something to double check. And we'll do all this in blue. Hopefully you guys can see this and it helps keep it clear for you. So for our total power, we can use E times I. We can take this times this. We can take 3,000 times 14.997. Or if you've been saving it in your calculator, which probably the best bet on a lot of these, especially as they get more complicated. This circuit is going to have 44,991,575 watts. That's how much power this thing's going to be dissipating. Pretty big number, but we have a high voltage. With the resistance, it's going to do that stuff. It's a bad boy though. So if we move it, 1, 2, 3, 4. Keep it all in mind, moving your numbers around for your calculations and stuff like that. Whatever they ask for, just pay attention to it so it doesn't come back and bite you later. So, since we know our voltage here, let's just go through and start solving for some of these. We're going to take E squared divided by our resistance of 10 So this 10 ohm resistor is going to be dropping 999.620 watts. This guy down here, 499.810. Now that might kind of throw you a little bit for a loop. It might seem a little bit odd. But you do have to remember that the more current that's getting opposed, the lower the voltage, all the numbers are going to work out this way. So another quick way to actually throw a check on these, which you're going to hear me keep saying, don't not do it, just go that route. Why not? Let's see, we can take these numbers and punch them up together and add these together and just use this resistor to see if we're in the ballpark, see if we got it. Which, looking at it, we got 14.99 is what I got. Roughly, looks like it's almost right on. So we're good on that one. We know we can move forward. So the next one over here, we got 599.887 volts squared divided by 40. And so on and so forth. We can just go right through and go right to town punching these things in to see what we got going on. Pretty straightforward, not too bad. And we'll leave this and just punch this one out real quick, so it's right there and it's asking for it. Then we'll take this 50.552 So this one up here, we are going to be dropping 34.073 watts. $127.775 watts. Well, those are terrible looking fives. And obviously these last two should be equal because they're the same resistor. So just quickly looking at it, does it look like it's something that should add up? Does it look like it makes sense? Kind of jumps around, but numbers look like they make sense. The higher the resistance, the lower the wattage on it. Because we're applying that many volts to it, that's about how it should work, because current and everything is proportional, or indirectly or directly proportional. Stuff just to keep in mind for terms. So let's quickly add these up and just see how it kind of adds up. A little off, but not too much, off a few points. Yeah, not too bad. So that's our wattages. Well, for our currents, we know it's constant in a series circuit, so we know right off the bat, we'll do this in red, hopefully it's nice and easy to see. We know that this right here, our IT is going to be flowing through this part down here. And over here. We know that that's the only path for current to flow, so it has to go that way. So now we want to solve for current, which we can use P divided by E or E divided by R. So let's use our E divided by R. Let's go that route. So through this resistor up here, we're looking at 9.998 amps. And let me label stuff after I tell you guys you got to do it, and then I totally just pass it off and don't do it at all. Okay. Okay, so let's look at this quick. I know it's a shitty 4. So that's roughly 5. Roughly 5. We're in the ballpark. Seems like it's pretty damn close to this. The rounding might have thrown it off just a touch on these because I didn't round on those. But it's looking like that's the same current flowing through, which makes sense. As long as that's all adding up and jiving, you're in good shape. So let's start going through this guy down here. So we know it's 50.552 volts. So for the 75 ohmer on the top, it's current. It's going to be 0.674 amps. Through here, through the 20 ohm resistor, it's going to oppose current less, so it's going to go up. So numbers are still making sense. Ground in 3 places. Down here, we're looking for this resistor. It's going to be coming out to 5.055 amps. .370 amps. And the last one, you might as well punch it out because it ain't going to hurt anything. Maybe you hit a key wrong, which I do that quite a bit myself. So, that's what we've got for that. Let's go back through and add up what we have and make sure that we're in the ballpark. Should be pretty close to what we're actually punching through. So on my calculator, I punched out to 14.9971. So I'm right there. For our currents, our power through each resistor. And you see current divides up. The highest resistor, the least amount of current goes through that. So keep that in mind. And you see it's being applied the same voltage, but you see the wattage coming out of that. It really changes it by how much current can get through there and how hot something's going to get essentially. A resistor is essentially going to throw off heat. So this is that practice problem that we did again. If there's any questions on these, you guys want to see some more of this stuff, let me know. We can throw another one up and go about it. All right?